Let's look at some examples that involve sorting. So first of all, I'm going to do an order by. That's how we're going to do the sort, obviously, but I'm going to do it without any indexing. So I'm going to drop both this first name and last name index. And then it's a simple query. I'm going to ask it to explain a select star from employee again, and I'm going to order by last name. You can see the output from pgadmin shows us a sequential scan through the employee table because we got to get all the rows, and then we're going to hand that into a sort operation. So the underlying node here, indicated by this arrow, is going to do a sequential scan on employee, and these values should look familiar to you by now. We're going to take 164 units to read all 10,000 rows, and the width is 21. Now we're going to do a sort operation. You can see here that the sort node, when indicated graphically here, has some familiar figures in it, right? The number of rows that it's going to have to deal with is 10,000. The width of each row is still 21. But now the cost estimates are really interesting. Whereas the sequential scan node can start giving back values immediately, right? If that's all we were doing, as we've seen. The sort itself can't do that immediately. It's got to do some work on the underlying rows from the sequential scan before it can start giving back any values at all, right? It has no notion until the sort is complete which is the first row that needs to be returned. So we can see here that its cost estimates are minimum startup cost of 828 units. So there's quite a lot of work that's being done between the 164 units that are going to come back from the sequential scan and the first row that's going to be available from the sort. And then it's going to extend up as high as 853 units. And again, the number of rows and the width of each row. So this is a pretty expensive operation. We are not giving the database any help, right? We got rid of the indexes that had previously ordered things by first name and last name potentially, and just asked it to do the sort. So it's going to do this on the fly. It's going to pay the cost of doing that sort every time you run this query. Now let's add an index. So create index if not exists employee first on the first name field. Same query, select star from employee, order by, well, I guess I'm doing last name here. Here I've added an index on first name, and now I want to index by first name. Now the index is already out there and it's sorted by first name. And what I'm asking the database to give me back is a list of employees sorted by first name. So I've already done the work ahead of time when I created the index. And what I see coming out here is reflective of that fact when I ask for this query. So I'm getting an index scan that's using the employee first index that I've added up here if it wasn't there on the employee table. And we can see here now, instead of having to wait until cost time 850 something, we're going to be able to start returning values from the previously indexed employee table very quickly, 0.29, which sort of sounds familiar. That's probably, again, some kind of a delay necessary to start getting the first values or the first pages that contain the index. And it's going to be done at time 570. So this will be completed well before the previous example even got started generating output, because we're leveraging the ordered nature of the index on the field that we happen to be asking for the database to order by. So again, when we ask for the query here, when we ask for this order by, the database's query planner is going to look around and say, hey, do I have any resources that I can use to make this go fast? Oh, look, the query is looking for an order by first name, and it just so happens that I have an index already defined that is ordered by first name. So it's just going to walk through that index, pull the information out of the index a page at a time as it goes, and then use that information to go and fetch data out of the underlying employee table and return those rows in the order determined by the index. Now there's still a lot of disk I/O and stuff going on there, right? This is not as fast as just returning all the rows from the employee table in whatever order they happen to have been stored there, right? That takes 164 units, as we've seen. So there's going to be more disk I/O to fetch the index out of disk, to continue to go back and forth between the index and the underlying table. So it's going to be more expensive, but it is not as expensive as what we had here, where the database is saying, hey, somewhere between 164 units and the beginning of my ability to return rows to you, I've got to actually read these things all in and sort them. So we don't have to pay that cost anymore. We can start getting data immediately, and essentially immediately, right after 0.29, and be done way sooner because we already have that information. Now, one of the things that you might be asking yourself is, why wouldn't we always just want to do indexing? In what we've seen so far, it seems like a uniformly good idea to have indexes that correspond to the kinds of queries that we're going to do. And that's kind of true when you're only thinking about queries. So an index being present is almost uniformly going to be beneficial to some types of queries. On the other hand, when you're trying to make changes to data, you also, in order to keep the index consistent with the underlying base table, you also have to update the index, which is expensive. So you don't have to resort all of the data, but you've got to figure out some way of making a change to the underlying data. So somebody puts in a different first name. Now you've got to go to that first name index and rejigger it so that the row appears in the appropriate sequence with the new first name. And that's not free. So what you normally do is define indices when you have an application that's going to be very heavily oriented toward retrieving information from the database. If you've got some kind of an application that's logging like register activity in all of your retail locations, where there's just going to be a ton of very small, very rapid insertions going on to keep track of things that customers bought at your stores, you probably don't want to run an index on that table. You just want to have those records show up in the database as quickly as possible, so you can not get behind the ball in terms of processing those requests rapidly. On the other hand, if you've got decision-making information that's going to allow a sales manager or a manufacturing manager or some other executive to query the data 50 ways till Sunday, and that data isn't going to change much during, say, the business day, then you probably want to take the time to put those indices in place so that those kinds of queries go quickly. So as usual, there's no free lunch. Indices are great for queries, but they're expensive when you're going to do any kind of modification to the data. And I've cited some examples about making changes, but it's also true for inserts. It's also true for deletes, that you've got to keep the index in sync with the underlying base table. In fact, in some cases, if you're going to do a lot of changes to the underlying table, it can be faster to throw the index away, do a drop index, then change the underlying table, and then create a new index on the updated data, whether you're updating, inserting, or deleting. That might actually end up being more rapid than having to do a bunch of changes to the underlying table and keeping the index up to date as you go. All right, let's take a look at range queries. What do I mean by that? Well, things where we have a comparison that's not an equality comparison. So here's the underlying query. Select from employee where first name equals first 300. So I've got an equality query and then a range query. Last name less than last 100. Okay, and I'm going to get rid of the first name index, and I'm going to define the last name index. So the first name, no index there. Last name, there's going to be an index there. We can kind of predict in advance that the index for last name is going to be really helpful in terms of finding those rows from the employee table that satisfy this criterion, because the last name index is going to have those last name values in sorted order. But for the first name, not so much, right? Because we don't have an index on that first name. So no matter what kind of query or what kind of comparison we're doing there, there's no index to help out. So here's the query plan. Let's again start from the lowest node. Again, here there's just two nodes, two bitmap operations, one an index scan and employee last, and this is going to use. So this is using that index, right? The employee last index that we defined right here. And it's going to immediately be able to give us back data because it sort of knows where the first one is, and it's going to give us information. It's going to cost up to 5 units of time. It's estimating 81 rows, and again, the width is 0 here because we're fishing information out of the index, not the underlying table. And then that can be handed on to the upper level query, which can only start when the underlying query is done, and it's going to do an additional check to filter out the first name on each of the rows that come back from the last name. So here we've got, it's a similar example to what we talked about before. We've got a partial index. We're only indexing one of the fields that we're doing a comparison against, not both of them. So we get a win, right? It's still now only 73 units of time instead of 164, but it's not a huge win. All right, so now let's actually index both of these things. So same underlying query, I formatted it a little bit differently, but we're still doing an equality comparison here and a less than comparison here. But now I'm making sure that I have indices on both the first name and the last name. So we get a little bit more elaborate situation going on here. So first of all, we'll start here in the innermost nodes. We've got a node here, and it's a bitmap index scan on the last name. And you can see that the cost estimate is quite similar to what we saw in the previous example because it's the same operation basically. It's going to give us 81 rows. There's going to be a width of 0 because it's the index. And then we can see the specific comparison it's going to do. And that's actually captured in this diagram in this node, right? The last name information is going to be coming out of that node in the query plan. Because we now have an index scan, or excuse me, an index defined on the first name, we can also do an index scan on that field. So we're now doing a comparison against an equality comparison for the first name, and we can see that we're spending between 0 and 4.4 units of time. We're estimating 24 rows that have a first name of 300. Again, don't be misled by my dumb convention here. These might be all the people whose first name is Joe or Sue or something like that. So those two things are going to be done kind of in parallel, and we have those two pieces. Now, this is where this kind of bitmap thing kind of comes in handy. If we represent in a bitmap those rows from the first name subquery and from the last name subquery, what we want to do is find rows that have both of those criterion satisfied. So if you imagine a bitmap, right, here's our bitmap for employee last, and I'm obviously not going to draw 10,000 rows here, but if this is row 0, row 1, row 2, row 3, row 4, and so forth, and what we're saying here is that each of these boxes in this array can hold a bit, and that bit is going to be true, set to 1, if the corresponding row happens to have met this last name criteria. So maybe we have zeros in this whole thing except for a 1 here and a 1 here and a 1 here and a 1 here. The same thing is going to happen here with this other leaf node of the query plan. It's going to generate a different bitmap, and I'll try to make the tracks line up here if I can. Again with row 0, 1, 2, 3, and so forth. And let's say that the pattern that comes out here 5, 6, 7. Let's say the pattern that comes out here is got a 1 here and a 1 here and a 1, so 4, 5, 6, 7, a 1 here. Okay, so these ones represent those rows that satisfy the first name criterion, this guy, and these ones represent those rows that satisfy the last name criteria. And what we're going to do then is AND together these two bitmaps. So when we look at the values here, we're going to see that we have a 1 here, a true, ANDed with a 0 or false, so that's going to be false. But here for row 3, we've got a 1 in this bitmap and a 1 in this bitmap. So the result here in this bitmap AND is going to be another bitmap where the corresponding rows, or excuse me, corresponding elements in this bitmap, so here's 0, 0, 1, 2, 3, because I've got a 1 here and a 1 here, I'm going to have a 1 in the final bitmap. And that's going to say that row 3 satisfies both this criterion and that criterion. So given that bitmap, I can go and look for that particular row in the underlying employee table and fetch that back as part of my result set. And that's going to continue here through the entire bitmap. Any place there's a 1 in this bitmap and there's a 1 in this bitmap, there'll be a 1 here, and then we can just go through this bitmap and use that to fetch in the details of the underlying employee table. So that's where this bitmap AND node comes from. And you can see that it's going to start at 9.61, which is a little bit after these guys get done. It wouldn't make any sense for it to start sooner than that. I'm not entirely sure why it waits that long. And it's going to be done almost immediately, right? It says 9.61 to 9.61. And then that's what's going to feed the the scan of the employee table itself. So this thing gets done at 9.61. The cost startup for the scan that's actually going to give the employee data back starts at that point, and it's estimate to have to take 13.6 units of time. And it's estimating here that there's only one such row, and the width is as we'd expect it to be. So again, the lower level nodes, the things that are more indented in this textual representation, are responsible for kind of creating data structures that allow the higher level nodes, as we move our way up in the query plan, to do their job more efficiently. Let's look at a join query. So first of all, we're going to throw away any index files just to avoid them clouding the picture here. But we're going to do a select from the city table, and there's a city and a country here that are connected where the city's country ID matches the country's country ID. So this is a foreign key, that's a primary key. And I want to find all of the cities whose name is less than city 50. So there's no index that's going to help with that comparison. We're basically just going to have to look at all of the cities. Now, conceptually, again, if we think back to our experience with the relational algebra, we know that all joins involve a Cartesian product. And I said that although that's logically what's going on, and then we're sort of filtering the rows from that Cartesian product, that's not actually what's happening in the database, because that would be super inefficient. Instead, we're going to make use of some hashing. So here's the query plan for this query. And let's, again, start kind of at the inside with the lowest level nodes in the query plan. We can see, first of all, that we've got a sequential scan on the country table. So we're just going to load in all the countries. And that's what's shown in this node of the plan. Now, while that's going on, as suggested by this next higher level node in the plan, we're going to be creating a hash, so a hash table, just like you're used to thinking of from the data structures, that is going to have information about the specifics of that country table. And it's going to be used when it comes time to do the actual join, which is going to be indicated here. Okay, so we've now got a country, all the country tables loaded, and they're referenced by an in-memory hash table. I guess it would also be possible that if the country table is very large, or if we had another table that was very large, that hash could be either in memory or on disk, but we'll just assume that it's in memory. Okay, now the next operation is this sequential scan of the city table. So we can see here, we're going to load in all the cities, and we're going to filter based on the filter criteria from the query. Remember that we were going to get all the cities that had names less than city 50. Again, it's just this dumb pattern I have for generating city names. Because we don't have any indices defined, we have no choice but to scan all of the cities and just test each one to see if it happens to match up with the filter criterion. Okay, so now we've got all the cities in that correspond to those whose name is alphabetically less than city 50. We've got all the countries in, and they're stored in a hash table that makes it quick and easy to look stuff up. That's going to then feed into this top level node. So for each of these rows that are coming in the sequential scan of the city table that survive the filter criterion, the top level node is going to look up to see if that particular city satisfies the hash condition, to see if there is a country that matches that city. So I've been kind of playing a little bit fast and loose with this hash table here for countries, but what you can see here is that the hash table is going to be hashed by country ID, right? It happens to be the primary key here, but that's sort of just accidental in this case. What we want to be able to do at this level of the query, this top level of the query, is for each city that survives this filter, we want to check to see if the city's country ID matches any of the country's country ID. Of course, we know, because those are a primary key foreign key relationship, that there should be only and exactly one country per city, but that's irrelevant in the sense of the query plan. So the hash condition is we're going to check to see if that's satisfied, and if it is, we're going to then do the join. So unlike what you might think of from relational algebra, where we thought about the Cartesian product being done sort of first and then everything else gets filtered out, what we want to do is sort of flip that on its head. We're going to filter out all of the irrelevant, well, in this case, we're filtering out some of the cities themselves because of the where clause, but we want to filter out any joins that we're going to potentially create where the join criterion does not hold true. In other words, if we're not going to join together all of the cities that survive the where clause with all the possible countries. We're only going to go look in this underlying hash table that we created down here to find those countries that have the country ID that corresponds to the city that we're working on right now. So that's what's really taking place here in this join itself, to kind of finally come out with the list of rows that satisfy all these criteria. And let's take a little look at the timing going on here. We can see, first of all, that the sequential scan of the country table is relatively quick because there's not that many countries. There's only 109 of them. And then the hash operation itself shows that its start time and its total time are the same. Well, that's probably not true. I mean, in the sense that there's some time taken to do the hash. But in practice, what's going to take place is that we're going to create this hash table as we're reading in rows from the country table. And because the disk I/O is really slow, we're basically going to get the construction of the hash table for free. So 2.09 is an important number here, and we can see that we have to wait for that to get done before we can actually start doing the join. So the top level node, the actual hash join, doesn't start till 3.45. There's some other overhead going in there for some reason. But it would be surprising for us to see this thing try to start before that underlying hash table has been completed, because at that point it wouldn't be able to check to see if the join criterion was satisfied. And then we can start returning rows from the city table right away, subject to this constraint. But if we assume that the constraint holds, potentially we're going to be returning rows from the city table immediately. And then that's going to go up to time 12.5, which apparently corresponds to the larger number of rows in the city table. And then that also is consonant with the notion that the overall join takes 16.2 units. It would be surprising to see this take less time than would be taken by the total time to bring in the city table, because we've got to look at each of the cities that satisfies the filter criterion to check, does the join condition hold between that city and any of the countries that have been loaded into the hash table below. So again, a pretty elegant way to deal with this problem that doesn't require us to do an actual Cartesian product and then filter on that. We're only going to load information in that we absolutely have to, like the list of countries here. Notice also that the database was smart about which of these two tables it loaded into that in-memory hash. In particular, it selected the smaller of the two tables for that operation. Even in this case, we see that their number of rows estimated coming from the country table was 109, which is the actual number, I think. And then the number of rows from the city table, this is actually an underestimate, because that's a guess of how many rows from city are going to survive the filter. There's actually quite a lot more cities in the database. And if it had loaded the city table into the in-memory hash table to do comparisons against the country, there'd be more work being done to create that hash, and more work being done to check the contents of that hash for each of the countries. So it figures out the appropriate ordering to bring in the smaller country table and hash it, and then compare that with the city rows that survive the filter on the city name. Let's look at a query that does aggregation. So here's my query. I'm going to do select count star from employee, where the first name is less than that faked up first name. And I'm also going to have an index in play here, so I'm going to define this index called emp first on the first name field of the employee. So let's take a look at the query plan. Again, we'll kind of start from the inside out. We can see here, first of all, that there's a bitmap scan using that emp first index to fish out all the rows that have a first name that's less than that string. Now, what that's going to do is give back a list of, basically a list of the pages that contain rows that satisfy that criterion. Disk pages in this case. I've been kind of finessing that issue so far. That information then is going to be fed into a bitmap heap scan, which is going to actually look at the real employee table. because the employee table is going to be searched in sort of an arbitrary order, right? We might be moving around from page to page to page. There's going to be multiple pages that are going to come in from disk that may have rows that satisfy well, they're going to have at least one row that satisfies the where clause, but they may not all satisfy the rows that have the where clause. So we have to do a little bit more work with those rows that come in on the same page as rows that were indicated by the index, and make sure that we're only keeping track of the ones that satisfy that criterion again. So we're only going to have to look at the rows that appear on that particular page of the disk, so that's a lot less work than having to scan the whole thing directly using a sequential scan, but we still have to just sort of make sure we're counting the right things. And then finally, the aggregation node is really just a count, right? So because the query planner knows that it's doing this with the purpose in mind of coming up with a count, it's probably keeping a counter busy the whole time that it's doing that. Let's look at some of these other pieces of output. So the width of these underlying queries is both 0. Remember that all we're doing is kind of trying to fish up the specifics of the count of the rows that satisfy that particular criterion. We don't actually have to bring in the data. We just have to count them up. So the width is going to be 0. We get some estimates on the number of rows. Here in the final node at the top of the query, we get a width of 8 because we're going to return a result set that has that count in it, and there's only going to be one such row that contains that information. And then the timings line up pretty clearly as well. We first of all have to do that index scan, so the index scan can start returning stuff basically right away from the first page of the index, and then we're estimating that's going to take 4.94. And that's going to feed into the scan of the actual pages. So this is going to start, it's 4.96, right? It has to start after this is done. And it's going to take 73 units of time because it's going to have to wander across all of the pages that were returned by the details of the index. And then once that's done, 73.43, we basically do the aggregation immediately, and that takes very little time, probably within the error of the measurement, to return the final aggregation. So you can see here in the diagram we've got an employee first index scan, and then we're doing a bitmap heap scan, and then finally the aggregation node, which is new here, is really quite simple and fast. Finally, let's talk about this variation on the explain command that is called the analyze option. So we can add this to an explain command, and what's going to happen is, well, several things. First of all, when we do an explain without any other decorations on it, what's going to happen is the database is going to run the query planner and come up with its best guess as to what the optimal query is and give us that information, and then it's going to stop. It's not actually going to run the query. It's going to just guess or show us what it would guess if we did choose to run that query. Well, what the analyze option does is allows us to get some more information about the actual behavior, the actual performance of the query. And what that means is that we're going to get information about the query plan's estimate as well as the detailed statistics and timing of the real query. So the main difference here is that the query is actually going to be run, okay? And we're going to add some statistics to the output from the explain command that are going to allow us to sort of validate, did the planner come up with the real value? Be careful, right? This is actually going to execute the query, right? So if you're trying to figure out the query plan for a delete statement, or an update statement that's going to go and clobber a bunch of existing data, you probably don't want to do in Analyze. You probably want to do this on a test database or something that's not going to damage production data. If you really, really have to do this on data you care about, you can leverage the transaction idea that we've talked about. So here's an example of running explain analyze, and we're going to use or detail that in a second. But I've wrapped that up inside of a transaction that starts here and then immediately does a rollback. So even if we were deleting a ton of data, because we're actually inside of a transaction here, when the analyze command ran the underlying query, we would basically roll back those changes without losing any information. Still probably a little dodgy to do something dangerous on production data. It turns out that the explain command can take other options in addition to analyze. One that you might want to try out is called verbose. It kind of gives you some more information, more detailed information when you're looking at the output from the query planner. You can get information about the disk buffers that are being used in memory. You can get more timing information, and then you can also specify a format. Like if you want to get this information in a JSON format to be able to use by some kind of visualization tool, that's available to you. But we aren't going to look at those things in detail. So here's the example that we'll use for analyze. First of all, I'm going to create indices on both first and last name of the employee table. And then I'm going to select all the fields from employee, and then I've got a where clause here that's got two conjuncts using a range comparisons, which is obviously going to leverage the indices. I've got an order by, and then I'm just selecting all of the fields and explaining that. So first of all, this is just the same kind of a run that we've seen before where I'm just doing an explain. And here's the query plan that comes back. You can see that we've got, again, at the lowest level here, we're doing a bitmap scan on employee last name to check that comparison. And then we're doing a bitmap heap scan on employee. And we're also checking to see if the last name works properly as we did before, the recheck. And then we're filtering on the first name. And then that information can be passed along to the sort, which is where the result comes back. So again, select all of the rows that satisfy this where clause, those two conjuncts, and then an ordering operation. So we get the read of the index, the read of the table, and then the sort operation. And if we look at some of the statistics here again, we can see that we can start returning rows immediately from not rows, but the details of the index from the index right away. Once that's done, our next operation can start here to scan the employee entries and compare against the first name, just like we did the last name down here. That's going to take up to 73.5, and then after that we can run our sort on those two criteria and return the final 47 rows. Okay, so that's pretty similar to what we've seen before. Now let's turn on the analysis information. So in this case, we're doing a select statement, so we're not going to make any changes to the database anyway, so we're safe there. And you'll notice that I've just added these two flags to the explain command itself. I'm saying explain analyze, and I also want to get information about buffers just to show you that you can get added stuff. If you don't use some of these more esoteric options to the explain command, you can actually just say explain space analyze space select, but this is the more complete syntax. All right, so now you can see we're getting a bunch of additional information. Same basic ideas, right? You can see down here that there's our bitmap index scan using that last name index, and we get the same kind of estimate values that we did before. But now we also see the actual times, right? That this took 0.41 milliseconds, returned 36 rows when in fact we expected 81, so it was a little bit off there. And you have the criteria for the comparison. Similarly, when we go up to scan at the next level of the query plan, we get actual times here from 0.58 to 0.169 milliseconds. Again, this has to happen after that's completed. And we get some additional information like how many rows were removed. This is because of the additional request for buffer data, number of blocks, some other things. But you can see that we're doing not so great here. We estimated 47 rows. We actually only got 19. I mean, whether or not we're doing good in terms of, or whether the query planner is doing good in terms of estimates is really kind of a judgment call. It's guessing without any additional information than what it's stored in terms of metadata about the database. And it's not like wildly off. It's not orders of magnitude off. So, that feels pretty okay. And then finally, the sort itself. And we can see that it actually ran pretty quickly. It only had to deal with 19 rows, which is why it was fast. It gives you some information about, like, here's the sort keys, here's the method that was implied. It used a quick sort algorithm and only had to occupy 26 kilobytes of memory. So again, you get more information about the actual behavior of the query, which can be really helpful if you're thinking about how do you optimize this This number is really kind of interesting, right? You can get a sense for how much RAM it's going to take to actually do that sort in memory. If you're doing much larger result sets and sorting them, you'd want to be concerned about that value to see, at what point do I hit a limitation where I need to add more memory to my server, or I need to do the query in a different way to avoid using up a ton of RAM.